So let's say we have F be holomorphic in C, the complex plane, except possibly finite number of isolated singularities, right? So there are finite isolated singularities, but you also consider infinity as a potential isolated singularity. Then what Cauchy's theorem tells you is that the sum of residues of F at these points, including Z1, Z2, up to Zn and infinity, the sum of the residues is always 0. Right? So if you also take the residue at infinity, then the sum of the residues is going to be equal to 0. Now why is this useful? Right? So the reason why this is useful is the following. Because the sum of the residues is equal to 0, right? I have given the proof over here, but the proof is literally the same that you typically see in a complex analysis course, except that we also have to take the residue at infinity. And the residue at infinity, the fact that it is minus a minus 1 is what sets the stage. But why is this useful? The reason why this is useful is the following. Let's say you have to compute a contour integration, but the contour integration has 10 poles inside, right? But now what I can do is, because I know that the sum of the residues, including the finite poles and the infinity, is equal to 0, instead of computing the poles at these 10, instead of computing the residues at these 10 points, all I can do is compute the residue at infinity and then use this residue theorem in this general sense. Right? So instead of doing 10 calculations, I am only going to do one calculation, which is the residue at infinity. That's the advantage. Okay? So what is the proof over here? So the proof over here is the following, right? So let's say there are these finite singularities, right? Z1, Z2 up to Zn. Now you consider a circle, right? A circle that encompasses these following. That 1 over 2 pi I integral mod z is equal to r f of z dz is equal to the sum. These are all finite. You see, Z1, Z2 up to Zn. This is just Cauchy's theorem. This is just Cauchy's theorem. Right? And this integral is equal to the sum of the residues at each of these finite poles. Right? Each of these finite poles. Okay? Now, what I need to do is I just need to compute this integral over here. This integral. But remember what we did in the previous stage. In the previous stage, I took this mod z is equal to r, but I gave this the clockwise orientation. Right? So when I did the clockwise orientation, the answer turned out to be equal to minus a minus 1. That is negative of a minus 1. But now I have given here the positive orientation, in the sense that this is a positive orientation for the region inside. So therefore this integral is now going to be not equal to minus a minus 1. This integral is going to be equal to a minus 1. So therefore what do I have? I have this a minus 1, which was the Laurent series, the coefficient a minus 1 corresponding to the Laurent series expansion in the region between mod z, between r and infinity. So that's a minus 1 plus is equal to this quantity over here. But now you just take this to the other side, so you get minus a minus 1 plus these residues is equal to 0. But we have shown that this is actually the residue of f at infinity. So the residue of f at infinity plus the residue at the finite singularities is equal to 0. That's Cauchy's theorem, including the residue at infinity. So the sum of the residues is equal to 0. But if you are only going to consider the finite poles, that's not true. You also have to consider the pole at the singularity at infinity. So if you also take the singularity at infinity, this is going to be the answer. So this is the Cauchy's theorem. The sum of the residues actually vanish. That's theorem. Okay. Now what into action? Okay. So let's look at this. N choose k. Right? Now n choose k, I can actually write this in the following integral. 1 plus z to the n by z to the k plus 1 dz. Why is this true? Because let's just expand this 1 plus z to the n by binomial theorem. So 1 plus z to the n is summation n choose k z to the k. Now you divide, or maybe I should not use k. I choose r. z to the r. R is equal to 0 to n. So now you divide by z to the k plus 1. Which term is going to survive when you integrate over this closed contour? Everything except r is equal to k is going to disappear. Right? So if r is not equal to k in this whatever I have written over here, if r is not equal to k, then the function is either holomorphic or it has a antiderivative. So antiderivative over a closed contour is going to be equal to 0. Right? So therefore the only term that's going to survive is the one corresponding to r is equal to k. That's exactly what it is. So now you see that I can use complex analysis with the combinatorial. This is the basic idea behind Egorychev. Okay. Now in some instances the following is going to be useful. So instead of looking at that representation, I can look at this representation. N choose k is equal to 1 over 2 pi I, 1 over 1 minus z to the k plus 1, z to the n minus k plus 1 dz. I will come to this in just a second. Actually, I will tell you why this is true. Now, let's say you want to find a function. So this is a characteristic function on between 0 and n. That is, it is 1 from 0 all the way up to n, and then 0 outside. Right? So let's say you choose n. So 0, 1, all the way up to n. At exactly these points, you want the function to be 1, and everywhere else we are only considering positive. So everywhere else it has to be 0. Right? So this is what is called as the indicator function or the characteristic function. So this characteristic function, you can actually write it in this fashion. Why is this true? This is quite easy to see, because see, mod z is equal to epsilon, right? So therefore, and if I choose epsilon to be small enough, 1 over 1 minus z as a convergent power series expansion. Then what is the expansion for 1 over 1 minus z? Don't be shy. Zero to infinity. Z power r. This is the geometric series, right? So now let's just consider. So what we have k plus r by z to the n plus 1. Right? Or in other words, this is going to be integral z to the k plus r minus n minus 1 dz. Mod z is equal to epsilon. Right? Now, if you consider over here, so this is r over here. So if r gets beyond, let's say n, right? R gets beyond n. That is, r is at least n plus 1. Right? If r is at least n plus 1, what happens? Somewhere here. If r is at least n plus 1, this is going to be holomorphic. Therefore, it's going to be equal. And if r lies between 0 and n plus 1, then you're going to have one term, exactly one term, which is going to give the integral. And that integral is going to be equal to 1, because we have also divided by 1 over 2 pi. So if you want to have, so why is this useful? Because you see that in some instances, you want to focus your sum to be between 0 to n, but it's better to treat the integral, it's better to treat the sum as from 0 to infinity. Why? Because suppose I were to consider this, right? Suppose I were to consider this from r is equal to 0 to, let's say, n only. Right? So then this is not equal to this. Right? This will have 1 minus z to the n plus 1 over here. Right? But what I can do is I can put an indicator function, this indicator function, and then treat the sum as from 0 to infinity. Okay. I have an example. If I have time, I'll show you. But anyway, so this is the basic idea. So I want to use combinatorics using complex analysis. Now, so this 1 over 1 minus z to the k plus 1, you can write it in the following fashion. N is equal to 0 to infinity, n plus choose k, n plus k choose k z to the n. So now let's go back. Right? So So what we have is, in the previous formula, we had 1 over 1 minus z to the k plus 1, 1 over z to the n minus k plus 1. So we have n plus k, choose k, z to the n by z to the n minus k plus 1. Right? Z to the n minus k plus 1. Or maybe I should use r. Sorry. Minus s choose L as a contour integral. And this epsilon is some positive number but small. Okay. So I have 2L minus s choose L. This is equal to 1 over 2 pi I. Now what about this power? Right. I'm going to use the first representation. So if I use the first representation, that's going to be 1 plus z to the 2L minus s. And for the bottom, I have z to the L plus 1 dz. Okay. Now this 1 plus z to the 2L minus s, let me expand in the binomial series, binomial sum. Right? If we expand this 1 plus z to the 2L minus s as a binomial sum, so you get r is equal to 0 to 2L minus s, 2L minus s choose r, z to the r. Okay? So then what I do is I also need to divide by z to the L plus 1. But once I do that, this is what I get. So look at this example. Right? So if I perform the summation over S, I just isolate all those terms which are independent of S and the one that depends on S. So for instance, from here, 1 plus z to the 2L, that comes outside. Z to the L plus 1, that also comes outside. What are the remaining terms? You have minus 1 to the S, L choose S. And then from here, I have 1 over 1 plus z raised to s. That's exactly what I have. Now this is independent of s. This only depends, these are the only players that depend on s. But this is a very familiar binomial sum. Right? It's minus 1 to the s, L choose s, a to the s. Which I know is 1 minus a raised to s. That's exactly what I have. 1 minus 1 over 1 plus z raised to, in this case, L, which is z by 1 plus z raised to L. Okay, but now once you substitute this, magic happens. So I have z over 1 plus z raised to L. That's exactly what I have. Right? This is what we found out here. Now, the terms outside were 1 plus z raised to 2L and z to the L plus 1. But now I just do some manipulation. I have z to the L, that goes away. 1 plus z to the L, that also goes away. So I have 1 plus z to the L by z dz. Now you expand this. If you expand this by binomial, I have L choose R, z to the R. But every term except the first term is going to disappear when you do the contour integration. And the first term is going to give you an integral 2 pi I. Integral to be 2 pi I, but I have also divided by 2 pi I. Therefore I get it. This is the basic idea of Egorychev. Right? Now, of course, the thing is, this is a very bare bones version of the basic idea. But the thing is, if you have a combinatorial terms involving 4, 5, product of 4, 5, 6, and then sum of those terms, and then you want to show that this actually simplifies to something else, something really simple. Of course, then you need to be very careful about the choice of contribution. But there is a combinatorial proof of this. What it's saying is the following. Let's say I want to choose from n plus m objects. I'm going to write 1 over 2 pi I integral mod z is equal to epsilon 1 plus z to the m by z to the k minus r plus 1 dz. Okay, and then what I have is I have this n choose r over here. So let me just put it back over there. So now what we get? So now what we get is, so we get n choose r, and then you have z to the r, and then you have 1 plus z to the m by z to the k plus 1 dz, and then integration. And this summation is over r, but now what I'm going to do is I'm going to consider r is equal to 0 up to n. And The reason why I can actually go all the way up to n is the following, is that if this k, so the combinatorial terms will adjust itself. If this r gets beyond k, right? If this r gets beyond k, this combinatorial term is going to be actually equal to 0. So what you can do is you can actually, without loss of generality, take this sum, so that technically the sum is from r is equal to 0 all the way up to k. But I can without loss of generality make it go all the way up to n. So that makes life simpler, right? So now what is this you have? Summation r is equal to 0 to n choose r, z to the r. This is equal to 1 plus z to the n. And then you have 1 plus z to the m by z to the k plus 1 dz. But this is 1 plus z to the n plus m by z to the k plus 1 dz integrate, but that is n plus m choose. I have it covered. Random or identity. This summation?
Identity.
Oh yeah, sorry, yes, thank you, yes, you're right. This is a typo, yes, thank you. There is no, it's just n plus m choose k. You're right. There is no summation over here. Now, you can also use, I'm not going to do this because I want to go into some more exciting stuff. So you can actually try this, that this sum, this combinatorial sum is actually can be simplified into this combinatorial sum. Again using Egorychev. Okay, this method. So let me not do this, but let me go into other interesting problems. And this is something that happens frequently in mathematics. And if you observe, right, you may not realize this, but you look at many of the proofs in mathematics, right? Many of the proofs in mathematics. So, for instance, let's look at Pythagorean theorem, right? All the known proofs that, at least to my knowledge, there are several. I think it now goes to 125 or something like that. But all the known proofs involve counting in two different ways, computing the area in two different ways, right? So when I was a student, my teacher told me this, that magic happens when you add and subtract a suitable quantity, right? So for instance, the fact that you have that the derivative, the Leibniz rule, comes from adding a suitable quantity, right? Adding and subtracting a suitable quantity. Or for instance, now a 2D integral, right? An integral in 2 dimensions. So what you have is that you do Fubini theorem, right? You interchange the order of integration. When you interchange the order of integration, miracles happen, right? So many different things come from changing the order of integration. Changing the order of integration is the same as changing the order of summation with a counting function, right? Looking at the same object in two different ways gives you a lot of insight into the problem. That's basically what I'm trying to say. Okay, all right. So now let's come back to this. So now what I'm going to do is the following. So I have the summation k is equal to 0 to n, this quantity, but I want to show that that quantity is equal to 2 to the 2n plus 1 plus 1 by 3. Right? 2 to the 2n plus 1, 2 to the 2n plus 1 plus 1 by 3. You see that the left hand side is a complicated combinatorial sum, but the right hand side is very, very simple. I want to give you two proofs and then stop over here. Okay? So the proof is the following. So let us set this f of n is equal to this. But now what I'm going to do is I'm going to consider a more complicated sum. Right? I'm going to multiply this with z to the n, and then I'm going to consider the summation in n. Okay, and then my whole point is, then after I have done a bunch of stuff, then I'm going to just isolate this f of n. In other words, what is the theory is that if you're just going to find this combinatorial term, that's going to be harder compared to finding the generating function associated to it. So what is the associated generating function? So let's consider f of n multiplied with z to the n. Summation n is equal to 0 to infinity. I have summation n is equal to 0 to infinity. This sum f of n already came with a k. K is equal to 0 to infinity of this term. But now you see that this is one of the points that I wanted to emphasize. You're going to interchange the order of summation, right? So if you interchange the order of summation, so I have k is equal to 0 to infinity, n is equal to 0 to infinity. Now I have this whole quantity over here. This whole quantity. Okay? So I have this n plus k choose 2k. Now I have set it up in such a fashion that that's the same as this n plus k. So I have 2z raised to n plus k, whatever this power is. Remember, k is fixed. In this summation, k is fixed. N is the variable. Right? So this n plus k over here runs from k to infinity. K to infinity. So I have this 2z raised to n plus k, and then I just have adjusted so that I get the same term as this one is. Okay? But for this I just need to use this particular formula. This was the derivative formula that I gave, although here, this one. So I'm just going to use this particular formula. You see that here m runs from 0 to infinity, choose k, that's the same as z to the k by 1 minus z raised to k plus 1. So if I use that, this is what I have. So k is fixed. Remember, k is fixed. This is fixed. So r choose 2k, 2z raised to r. And then I'm just going to use that particular formula. So if I use that particular formula, then I get 2z raised to 2k, whatever that power is. So whatever that number is, 1 minus 2z raised to 2k plus 1. Remember this formula. So if you have k, this is k plus 1. This just comes from the derivative. Okay. That's what we have over here. Okay. Now let us just simplify. I have summation k is equal to 0 to infinity. Z to the minus k, z to the 2k, that disappears, leaving you with z to the k. 2 to the minus 2k disappears. So what I'm left with is z to the k by 1 minus 2z raised to 2k plus 1. Now what I'm going to do is, I'm just going to write this in the same fashion so that I have a geometric series over here. So I have 1 over 1 minus 2z, let me just isolate that. And then I have z to the k by 1 minus 2z raised to 2k. But that's the same when you sum the summation, when you consider the summation from k is equal to 0 to infinity. This is a geometric series, which is 1 over 1 minus z by 1 minus 2z squared. Now we just simplify. This is exactly what you have. 1 minus 2z by 1 minus 4z times 1 minus z. Now you can split this into partial fractions. I have 2 by 3 into 1 minus 4z plus 1 by 3 into 1 minus z. Now what I'm interested in is in the nth coefficient. My goal was to find the nth coefficient of this f of n. Right? So all that I need to do is just look at the nth coefficient of this and the nth coefficient of this, and then consider the sum. What is going to be the nth coefficient over here? It's going to be 2 by 3. It's a geometric series, right? Summation 4 to the n, z to the n. Correct? From here. From there, it's going to be plus 1 by 3, summation z to the n. So the coefficient is 1 by 3. This 4 to the n is 2 to the 2n. So it's going to be 2 to the 2n plus 1 the whole by 3 wanted to. Plus 1 over there, 1 over 1 minus z raised to 2k plus 1. And then you have n plus k minus 2k, that is n minus k plus 1. I'm just using that particular formula. Okay, so then what we get 1 over 2 pi I, 2 to the n, 1 minus z, right? And then you have z to the n. But now I just need to consider the summation in k. This is summation in k. So the summation in k is going to be what? It's going to be, there's a 2 to the k in the bottom, right? 2 to the k in the bottom. So it's going to be a geometric series. That's what I'm trying to say. So what we have is 1 over 2 to the k, 1 minus z raised to 2k, and then z to the k. So that's going to be the kth term in the geometric series. So I have 1 over 1 minus z by 2 into 1 minus z squared. We just simplify. I have all these terms. So you just simplify this. You're going to get 2 to the n plus 1, and then 3 to the z to the n plus 1. So this is just splitting into partial fractions, right? So I'm just going to split this into partial fractions. So this is what I have. And now we are back into the same story, right? Because you consider this geometric series expansion, this geometric series expansion, and this geometric series expansion. The only thing is that you just need to take a 2 out, and then you have 1 minus z by 2. So because mod z is equal to epsilon, that's small. So z by 2 is still going to be small. So therefore, geometric series converges. So therefore, you have. Okay. Now, one thing that I have not mentioned. I think I'm out of. Yeah, I'm allowed to take this k to go from. So ideally, you see that if this is n plus k equals 2k, right? Now remember that you have 2k in the bottom and n plus k in the top. So ideally, you would like to consider the summation from k is equal to 0 to n, right? K is equal to 0 to n. But I'm actually taking the summation from k is equal to 0 to infinity. Why? Because you see, let's say it gets beyond n. K gets beyond n. So then the top becomes, let's say, 2n plus 1.